going here. All right, so the domain then would be from.
You don't leave that as improper fraction.
Yes. Not going to change them to decimals or mixed numbers and leave them as impropers. So domain x, as long as x does not equal plus or minus 5 over 2. The interval notation to be negative infinity, negative 5 over 2, union, negative 5 over 2 to positive 5 over 2, union, 5 over 2 to infinity. So there's our domain. We've already got the factored form of the denominator. So when I go to simplify, I know that it's 2x plus 5 and 2x minus 5 on the bottom. What do I do to the numerator to factor it? How? Nope.
You
mean GCF?
Yeah.
Okay. GCF would be 12 and 30. What will go into both of those? 6. What else do they have in common? X. What's that leave in parentheses? 2x minus 5, which, hey, that happens to mark out one of my factors from the denominator. And so I get 6x over 2x plus 5. So again, the denominator set equal to 0. We're going to try to use factoring to solve those to help us find the domain of that. But that factoring, the reason we're using it is because it's going to help us simplify out of that. So always, to find the domain, you're setting the denominator of the original problem equal to 0. Try to use factoring to solve it because that's going to help you simplify later on. If you can't factor it, don't miss a problem that says just find the domain because you can't factor it. You know that you can use quadratic formula or square roots to solve some of these. Okay, so keep in mind that if it just asks for domain, you can solve the problem. If it says find the domain and simplify, you've got to simplify it. So the factoring is very important. But sometimes you can find the domain by just solving. That can help you at least narrow down your choices. Anyway, all right, so let's look at this one. Let's just simplify. Don't worry about the domain on this one. We'll get plenty of practice with that. Just simplify. Don't worry about domain. So, bless you. X squared minus 8x plus 16. And then throw a little curveball in it. 8x minus 2x squared.
You have to put it in order first.
Okay, good. That's not in order, so I'm going to rewrite that. And then do the factor. So because it didn't say anything about finding the domain, we're just simplifying here. You can start with the top or you can start with the bottom. It doesn't matter which one on this. So if I factor the numerator, the top part of the fraction, I'm going to use the x method. I need something that multiplies to be 16 and adds to be negative 8.
But it doesn't matter which one.
What do you mean? You're going to do both of them anyway. So you got to factor them all anyway. So negative 4 and negative 4. So that'd be x minus 4, x minus 4. And then on the bottom, how are we going to factor that?
You get in 2 and 1 x squared. You get a 4 out.
It's not a difference of squares. Common factor would be 2 and
4.
what else do they both have? X's. So here's the trick to this one. Because that leading term is negative, when you pull out the 2, you want to pull a negative with it so that it's negative 2x as the GCF. The reason you want to do that is so that what you've got left in parentheses doesn't have a negative in it on the front part. So what times negative 2x gives me negative x squared? 2x squared would be x.
Plus 4.
Not x plus 4, but x
Oh, did you get a minus?
minus, because yeah, to get that to happen. Now, how many of those x minus 4s on the top will cancel?
Well, you got 2.
I got 2 up there and 1 in the bottom.
But they're not squared.
Right. So 1 cancels 1. 1 cancels. It's a 1-to-1 cancellation. So one matching factor will cancel out the other matching factor. So that leaves us x minus 4 over negative 2x. That's a simplified version of that one. Another one that's kind of similar to that. 2x squared plus 7x minus 4 over 5x squared plus 20x. Doesn't matter. We're just simplifying, so it doesn't matter which one you start with. If you want to factor the bottom first, it's probably the easiest one to factor because it's smaller. 5x would be the GCF. Okay, 5x on the outside. What's it leave on the inside? All right. So that gets us the factored form on the denominator. If it asks us to find the domain, what do we do with that? It's already factored. Set it equal to 0. To find the domain, you set it equal to 0. So you have 5x equal to 0, x plus 4 equal to 0. So you get x can't be 0, x can't be negative 4. If it asks you to find the domain. Here we're just simplifying, so we want to factor the numerator, the top part as well. So we'll do the x for that. So that'd be negative 8 had to be 7. Negative 1 and 8. So it's 2x squared minus 1x plus 8x minus 4. And I'm grouping that. So what did 2x squared and negative 1x have in common? An x leaves 2x minus 1. What do 8x and minus 4 have in common? 4. I'm putting a plus 4. 2x minus 1. My factored form on the top then is 2x minus 1, x plus 4. On the bottom, we got 5x and x plus 4. What cancels? X plus 4s. Factored or simplified form is 2x minus 1 over 5x. You can never cancel part of a factor. Like you see this x here and this x up here. You can't cancel those because they're parts of a factor. You've got to either cancel the whole thing or none of it. So it's got to be a perfect match to cancel out. Here, this is not a perfect match. You can't cancel. Even if this was 5x minus 1 up here, it's not a perfect match because this is just 5x. So it's got to match completely to be able to cancel. Okay. All right. So simplifying is still going to be a part of everything we're doing right now with this stuff. The next kind of step that you take with the rational expressions is multiplying them. So let's look at multiplying a couple of fractions, just regular old fractions, no letters or anything in them. Let's look at 6 over 7 times 21 over 30. If we're going to multiply those two fractions together, what are the rules that you're able to do when you're multiplying fractions? You want to remember them. You can multiply straight across, top times top, bottom times bottom. What are not cross multiply, cross divide or cross cancel. So that means depending on who you have to teach what they call cross dividing or cross canceling. So that's like saying how many times does 7 go into 21? That's a cross divide or cross cancel. I think that's what you mean. And then the 6 and the 30, 6 will go into itself and 6 will go into 30. So that's how you can cancel. The ways that you can cancel when you're multiplying fractions are vertically or diagonally, never straight across. Okay, canceling can happen vertically or diagonally, but never straight across. The reason that you can cancel diagonally is, think about the factoring of 21 and 30. 21 is 7 times 3, right? 30 would be 6 times 5, right? Those are the same, that's the same problem, but just written as factors instead of as the product. So here, this 7 down here cancels that factor of the 7 right there. That's what's happening when you were able to cancel like that. So you're canceling. This 7 cancels that 7. This 6 cancels that 6, leaving us 3 over 5, because that's all that's left out of that. Had you multiplied straight across, 6 times 21, that's 126. 7 times 30, that's 210. And then you reduce from there. It still ends up being 3/5 at the end, but it's a whole lot bigger numbers to deal with out of that. So that's where the cross dividing and the cross canceling helps. When we start throwing letters in there, I think the cross canceling gets easier because you're just looking for matching letters, right? So let's get a pretty easy one here to start off with. Let's say we had 6x over 7 times 28 over 9x squared. So we want to think about this in the same way that we thought about this, for example, F. We think, okay, rules for canceling and simplifying are I can go vertically or I can go diagonally. Okay, so I look vertically first. It doesn't matter which one you do first, but I always try to go, hey, can I make it easier just up and down before I start crossing over? 6x over 7, does that reduce any? No. What about 28 over 9? 9, what are the factors of 9? 3, 6 doesn't go into 9. 3 and 9 and 1. Do any of those go into 28 evenly? 3 goes into 27 evenly, but not 28 evenly. 9 goes into 27 evenly, but not 28. 1 does, but it doesn't really help us any. Okay, so nothing I can do vertically. I usually will look, see if I can do something vertically first. Then I look at it and say, okay, well, nothing vertically worked, so let's try diagonally. So looking diagonally, I see the 6 and the 9. What number goes into both of those? 3. How many times does 3 go into 6? 2 times. So I can divide that and turn that into a 2. I can divide that and turn it into a 3, because 3 goes into 6 twice. So that's where this 2 comes from. 3 goes into 9 3 times. That's where that 3 comes from. What else can cancel?
The X is
We got how many X's up here?
1.
How many down here? 2. So how many get canceled?
1.
1. So this X cancels completely out. One of these 2 cancels out. So this X is gone. This X squared just becomes plain X. Okay. Now that's that diagonal. Let's do the other diagonal, 7 and 28. 1 and 4. 7 goes into itself 1 time, and then the 28 4 times. Now I've done vertically and diagonally. Now all I've got to do is multiply what's left. Top times top, bottom times bottom. 8 over 3x. And you leave it like that. That's right. You leave it like that. If you do all your canceling vertically and diagonally, what you have left should be done. You just multiply straight across, and you're done. Okay? Let's look at a little bit more difficult problem. Just got a little bit different numbers. Letter-wise, a little bit different. Let's say we had 4y squared over 18 times 27 over 8y to the 5th. So again, we're going to look vertically, then diagonally. Okay, it doesn't matter which order you do that in. I just like to do vertically first.
2y squared over 9.
Okay, because 4 and 18 are both divisible by 2. So we could simplify vertically there with the 4 and the 18. 2, and this becomes a 9. What about this other fraction? Can it be done vertically? 27 and 8. No, nothing goes into both of those. All right, now I can go diagonally. 2 and 8 have 2 in common, right? So it ends up being like 1 and 4.
4y to the 3rd.
Okay, because 2 y's up here cancel out how many down here? 2 of them, so 5 take away 2, 3. So these y squareds up here are gone. This becomes y cubed, or to the 3rd power. What about the 9 and the 27, the other diagonal? 1 and 3. All right, now multiply across. 1 times 3 is 3. 1 times 4 is 4. And then a y to the 3rd power. Gotcha.
So you don't have to put, there's no y to put across.
Yeah, because this one cancel out completely.
Total.
Yeah, totally cancel.
Well, if you can go vertically, you can go that route.
Yes.
Yeah.
Yeah, you've got to do both of them anyway. It doesn't matter what order you do that in, but you've got to do diagonally and vertically. Some problems won't have anything you can do vertically. Some won't have anything you can do diagonally. Some will just have vertical. It's just, you've got to do both.
Okay.
Look for both. Good question. All right, let's step into a polynomial kind of style one that's already factored for us, and then we'll add in the factoring. All right. Technically, I wouldn't have to have the parentheses down here in the bottom. I guess I wrote them out of habit. All right, so again, we're going to look at this problem. It's already factored for us. We're going to have to start factoring here in a minute. But the idea here is to cancel out things that can be canceled. And the rules are you go vertically. I'm a vertical first person. Some people are diagonal first. It doesn't matter. You got to do both of them. Okay? I see vertically happening pretty quick on this one. What is the matching factor vertically? Yeah, this x minus 3 in the bottom can cancel this x minus 3 that's up top. So that's a vertical cancellation on that fraction. Is there any vertical cancellation on the second fraction? Doesn't matches, so I can't do that. So the x minus 3 cancels the x minus 3. I've done all vertical. Now I got to do diagonal. What cancels diagonal? This x plus 4 cancels that x plus 4. Anything else cancel? No,
There's nothing left.
there's nothing left of this first fraction, right? Everything canceled out of it. So there's nothing to work with. Only thing left up top is this guy, x plus 5. Only thing left on the bottom, x minus 1. So that's it. That's all there is left. So that's what you have. Let's look at let's do this one. 4x squared plus 3x minus 10 over 2x squared plus 3x minus 2 times 2x minus 1 over x plus 4. Now, this is where we start getting into and be able to factor, be able to simplify this. Usually when you're looking at problems like this, if you're having to do the multiplication step, I'm not asking you what the domain is. Okay, I'm just asking you to simplify. So don't worry about domain unless it asks for it, and it's usually only going to ask for it if they give you one fraction. Do all of that in one. Okay, so first thing we want to do is factor any part that can be factored. So we look at every piece of the problem. So we look at numerator here and say, okay, can I factor this? If so, how? Well, is there a GCF? 1, that doesn't help us. So how many terms are there? 3. So that means we're going to use what?
The X.
The X thing, the X method for factoring that. So set up our X. What goes up top? Negative 40. That comes from 4 times negative 10. And the bottom is a 3. Multiply to be negative 40 and add to be 3. Negative 5, positive 8. Good job. That's right. Now, I can't use my shortcut because it's got the 4 in front of x squared. So I got to do it the long way. I got to do that grouping stuff. So I'm going to write it out here. I'm going to write 4x squared plus 8x minus 5x minus 10. Does it make sense that I put the 8 closer to the 4? Because I know the GCF, that's easy. And I put the 5 close to the 10 because I know 5 and 10 have something in common really easy. It doesn't matter what order you put that in, but have some common sense about it. Make it easy on yourself. So I'm going to group the first two together. So GCF of 4x squared and 8x. 4. And they both have what else? X. What's that leave in the parentheses? X plus 2. What do I pull out of the second pair? Kind of 5. Negative 5. Leaves us an x plus 2. So the factoring of that numerator. So I'm going to rewrite the problem underneath here. X plus 2 and 4x minus 5. That's the factoring of the top part. Now I've got to factor the bottom part. Got to work with it then. Okay. I'm going to use the X method on it. Negative 4, add to be 3. Adds to be negative 4, or multiplies to be negative 4, adds to be 3. Negative 1, positive 4. Technically, doesn't matter what order I put that in. I chose that order. Group. 2x squared and 4x have 2x in common. Leaves x plus 2. Those two have what in common? -1. Leaves x plus 2. So the factored form of the denominator is x plus 2 and 2x minus 1. This fraction over here, is there any factoring that can be done to it? No, there's not an x squared in it. There's not an x cubed or anything going on with it. So there's nothing I can really do to that. So I'm just going to copy it down here. 2x minus 1 and x plus 4. And then I'm going to go to cancel the things vertically and diagonally. Vertically, what cancels? X plus 2 on that one cancels that x plus 2. What else cancels? The 2x minus 1 on the bottom left and the 2x minus 1 on the top right. They're matching factors. That leaves us a final answer of 4x minus 5 and x plus 4. Okay. Now, let's do another. Experience. She's a good teacher. X squared minus 1 on top. X cubed minus 1 on the bottom. Let's do xy minus 2y plus 3x minus 6 over, and this is going to be a weird one, xy plus 3x plus y plus 3. But I think this will help you understand what you're doing here with the factoring with the multiple variables in it. All right, so let's factor everything. That's the first step. So I'm going to start with these two on the left. X squared minus 1. That is a difference of squares because it has x squared minus 1, and we know 1 is what squared? 1 squared, right? So that's a difference of squares. So I can go straight to the factors of a difference of squares. For that one to be x plus 1 and x minus 1. So kind of as you're doing more of these, you're going to be able to take some shortcuts and quickly be able to factor differences of squares. The one that nobody ever remembers, and I'm going to be impressed if you can tell me how to factor x cubed minus 1. Do this in 100. Sum and difference of cubes. Sum or difference of cubes. This is a difference of cubes. Here's the pattern. Because 1 is also 1, 1 cubed is still 1, right? So that we've rewritten it as should be a cubed right there, not a squared. Brain got behind my hand. So this is x cubed minus 1 cubed. That is a difference of cubes. The way that factors is it has a short piece and a long piece. Do y'all remember that? Maybe, maybe not. Short piece, x minus 1. Long piece, x squared plus 1 times x is 1x plus 1 squared is 1. sums and differences of cubes. I'll try to link a video on Canvas out to you guys on a review of sum and difference of cubes. Just because you don't do it very often, so it's not something you're going to remember a whole lot. I do it more often than you guys do for sure, but I still, even teaching math every day, I don't do sums and differences of cubes very often. They don't come up very much. Okay, so that's the factoring for the first fraction. Let's factor the second fraction. It's actually a little easier, even though it looks much more complicated because it has two variables in it, but it's much easier to do because it has how many terms?
Can you cancel out
4.
vertically?
We'll do that in a minute. Let's get the factoring all done before we start canceling stuff. A lot of times if you start canceling before you get all the factoring done, you'll over cancel, which is why I always wait till the end. So if there are 4 terms, we're going to do what? Group. So I'm grouping these two together. What's the GCF of xy and negative 2y? Y, so that leaves us x minus 2. GCF of those two would be positive 3, and that would leave us x minus 2. So the factors on the top are x minus 2 and y plus 3. The bottom part works in a similar way. The first group, x is the GCF, leaving y plus 3. What's the GCF of y and 3? What do they have in common? 1. That's the only thing. So that leaves us y plus 3. So that factor is y plus 3 and x plus 1. So the grouping makes that a very easy problem. It looks much more complicated because it has 2 variables, but the work's not hard. Now we can start canceling stuff. So I always try to factor everything first and then cancel things. So vertically and diagonally are the directions I'm going. So I've got vertical here with the x minus 1s, a vertical with the y plus 3s. Do I have any diagonally? That x plus 1 up top cancels that x plus 1 in the bottom. And that's it. That's the simplified version is x minus 2, x squared plus x plus 1. All that factoring. And it simplifies it out to do that. Nice and fun thing. If you can factor, it's actually, I think it is actually fun, but if you struggle with factoring, you may not think it's very much fun. All right, so the next thing after you do multiplication, we always do what next? Division. Okay, so here's the wonderful thing about fractions is when you're dividing, if I had 2/3 divided by 15 over 4, and I was going to do that without a calculator. Example L. What's the method that I use when I divide fractions?
Flip your reciprocal.
Of which one? The second one. So it's really 2/3 times 4 over 15, right? And then it's a multiplication problem, right? And then you could do that way, or you could cross cancel or cross divide to if possible. It doesn't on this one. So 8 over 45 is the final answer there. A division problem quickly turns into a multiplication problem, and there are no new rules. It's back to the same stuff we've just done. Okay, you just have to remember, hey, flip the second one, make it a multiplication problem, then do the work again, the same way that we did. Let's do an example of division. Example M. 5x squared minus 16x plus 3 over x squared plus x minus 12 divided by 30x squared minus 6x over 2x cubed plus 8x squared. Okay. Now, every year, in every semester that I teach this stuff, in 110 or my Algebra 2 class at high school or college algebra in high school, when we're teaching this, somebody always asks, can I factor it first before I flip it? Mathematically, yes. But most of the time, that kid that asks that question forgets to flip it. Because they get it factored and they've done all that hard work factoring and they get in a hurry and start canceling stuff before they flip it. So I always try to tell my students, flip it first and then do your factoring. Okay? So let's flip the second one, change it to a multiplication problem. So the first fraction stays the same. It stays as 5x squared minus 16x plus 3 over x squared plus x minus 12. And then the second one becomes 2x cubed plus 8x squared over 30x squared minus 6x. So flip it, it becomes a multiplication problem, which means, hey, I do it the same way we just did the last 14 problems. Or it seems like we did, but it seems like we did. And we're just going to factor it. Okay, so once you flip the second one, factor. So I know the bottom one here, it multiplies to be negative 12 and adds to be 1. It doesn't matter where you start factoring, just factor. So that'd be 4 and negative 3. So x plus 4, x minus 3. The top half of that fraction is a little more difficult. You still do the x method. Got a 15 on top and negative 16 on the bottom. That'd be negative 15, negative 1. But I can't go straight to my factors. I got to do the grouping stuff. 5x squared minus 15x minus 1x plus 3. Group that. 5x, x minus 3, negative 1, x minus 3. So that's going to be x minus 3 and 5x minus 1. Good news is the next fraction doesn't have x method stuff on it. It's just got GCF stuff, which is easier to do. 2x cubed and 8x squared, what do they have in common? 2x squared. There's two x's in common, so that'd be 2x squared, and they'll give you x plus 4. So 2x squared, x plus 4. Then on the bottom, what's the GCF of 30x squared and 6x? 6x. And that leaves you what in parentheses? What times 6 gives me 30? 5, and then x, and then a minus 1. And then once you get it all factored there, it's just vertical and diagonal cancellations. So vertical cancellations, I got the x minus 3s happening. And then diagonally, I got the 5x minus 1s. I got the x plus 4s. Ooh, what else? No, it's not it.
You can take them for 6x.
Yeah, this x and then this x squared. This x will cancel one of those. The 2 and the 6. 2 goes into itself once and into 6 3 times. So it's going to be 1x over 3. So that big ugly problem we started off with simplified down to just plain old x over 3. Quite easy on that. Once it gets here, it looks easy. But it started out as this big monster thing that took a lot of work to get there. So multiplication, the rules are factor, everybody, cancel vertically and diagonally. Division, the only difference is, what do you do first? Flip the second one. Flip the second one, and then do multiplication again. Same rules for it, okay? So that makes that a lot easier, because you're not having to learn a new set of rules for that. Now, we've done multiplication, we've done...
On the bottom, it doesn't touch that at all. And then the 5x minus 1,
The 5x minus 1 was canceled by that 5x.
it just leaves that 6x.
Leave 6x there, but then we could reduce that
You do
to
the 6
2
and
and
the
3.
2.
The 2 and the 6 become 1 and 3, and then this x cancels one of those x's. So that's how we end up with 1x on top, and then just 3 on the bottom because they're gone. Everything else has been crossed out.
Okay.
All right, so we've done multiplication, we've done division. The next thing is addition and subtraction. Those are the harder things with fractions. Addition and subtraction are harder than multiplication and division because what's the rule with fractions when you add and subtract? Common denominator. That's the hard part. Okay, so if we were going to add 3/5 plus 9/20, what would be the common denominator? 20, a number that both of them go into. So you got to have the same thing on the bottom in order to add it. Okay, now, so how is 20 related to the 5?
4 times.
It's 5 times 4, right? So this denominator has 2 factors. It's got a 5 and a 4. This one has only one of those. It needs which one? It needs the 4. So you have to multiply this fraction by 4 on the bottom. If I do something to the bottom of the fraction, what do I have to do? Do the same thing to the top. So I've got to multiply the bottom by 4 and the top by 4. So that turns it into 12/20 plus 9/20, which ends up being 21/20. So common denominators are going to be the name of the game. And that's just going to take some experience of dealing with it. All right. Example O. Let's do something with letters in it. 3/10x to the 4th power plus 2/15x squared. We're going to add these 2 fractions together. So the first thing we want to look for is the number in the front because it's not a factoring problem for this one because you don't have like x squared plus something else. The bottom part is just a monomial because you got one term. So we're looking for a number that 10 and 15 both go into.
30.
30, that's the smallest one they both go into?
Mm-hmm.
Yeah?
Yeah.
Because 15 times 2 is 30. 15 times 1 would be smaller, but it's not 10 that go into it. So yeah, 30 is the smallest one. Okay? Now, so we need to turn those both into 30s. So how do I turn a 10 into a 30? Times it by 3. So if I multiply the bottom by 3, I got to multiply the top by 3. How do I turn a 15 into a 30? Times by 2. I multiply the bottom by 2, I got to multiply the top by 2. Now that only takes care of the number. I've got to get the letter the same too. This guy has how many x's? How many does that one have? 2. Which one's more? So I need to match up that. How many more x's does this one need? Needs 2 more, so that's an x squared. So I've got to multiply that one by x squared as well. That gives us 9/30x to the 4th. 2 times 2x squared would be, I'll put an equal sign, plus 4x squared. And then 15 times 2 is 30. X squared times x squared. X to the 4. That makes it match up. 30x to the 4th. Once you get the denominators the same, then you can try to add the numerators. These don't have, they're not like terms, but I could just rewrite the problem. 4x squared plus 9 over 30x to the 4th. If they're like terms, you put them together. If they're not, then you Stack them up in there. Line them up. Stack them. Line them up. None of that. Okay? Go a little further. Let's look at one, maybe x minus 5 minus 2 over x minus 5. Got two fractions, we're going to subtract them. The rules for subtraction are that the denominators have to be what? The same. Are the denominators the same? Yes. Both of them are x minus 5, right? Do I have to do anything if they're already the same? No. All I've got to do is do the math that's on the top. What's 7 minus 2? 5. 7 minus 2 is 5. X minus 5 on the bottom. Done. Okay. Where they can get you when they do something like this. 6 over x minus 3 plus 4 over 3 minus x. My little dyslexic brain doesn't want to do this right. My brain will swap that second one every time. But it's not.
So they can be negative x plus 3.
Okay, that is, if we wrote it in descending order, it would be negative x plus 3. But does that match x minus 3?
No.
No. Okay, so let's take Cindy's lead here and say that's negative x plus 3 over 4. And this is 6 over x minus 3. Now, if I think about factoring that denominator, what could I factor out of this piece?
The 3.
No, they both don't have a 3. What do they both? What's the common factor between those two? Negative what? Both don't have an x. Negative 1. They both have 1 that'll go in common. But if I factor out a negative 1, what does that turn the parentheses into? A plain x, and 3 divided by negative 1 is negative 3. Doggone, that matches right there. But this negative 1's in the way.
But that don't matter.
Yeah, it does matter, because they're not the same. This is x minus 3. This is negative 1 times x minus 3. They're not the same. So we've got to make them the same. So what do I have to do to make them the same? Times what by negative 1? That other one, the whole thing, both top and bottom. So I multiply the top and the bottom by negative 1. And that gives me negative 6 over negative 1 x minus 3 plus 4 negative 1 x minus 3 well, what's negative 6 plus 4? Negative 2, negative 1 x minus 3. That's the common denominator, is negative 1 x minus 3. If that's the common denominator, okay, can I simplify that? Remember when we do fractions, we always simplify at the end. What about that?
1 is 2.
Oh yeah, negative 2 divided by negative 1 is 2. So that'd be 2 over x minus 3. That's the thing that's a little trickery that they try to throw in there, is when they swap the order and put the minus sign on a different one, and you've got to think factoring to fix it and get a common denominator, because they look so much alike, but they're not. No. They're always going to simplify. They're not going to leave it this way. They'll always simplify. Let's do this one. What letter are we on? R? R. You have 4 over x minus 3 x plus 5 plus 6 over x plus 5 x minus 5. So this one they're nice to us and everything's already factored for us. When we're adding, subtracting fractions, you gotta have what? Common denominator. So we look at the denominators, and the human eye and our brain is good at finding things that are the same. What's the same? X plus 5. So they both already have that part. But the first fraction has an x minus 3. And the second fraction has an x minus 5, right? So they're not the same. So, but they have one piece that is the same. I just need to make all the other pieces the same. So this one already has the x plus 5. It has an x minus 3. What does it need to get more like that one?
Needs a -2.
It needs an x minus 5. Remember, it's got to be a whole factor.
Oh,
Okay? So it has an x plus 5. It's already got that matching piece. We need an x minus 5 on this one to get it more like that. So it needs x minus 5. We multiply by that whole factor that we need on top and bottom. What does this one need to be like that? It needs the factor of x minus 3. Okay? So we multiply bottom times x minus 3, top times x minus 3. Okay? Now, both denominators have the same stuff in them. May not be in the same order, but it's the same stuff. Both of them have an x plus 5. Both of them have an x minus 5. Both of them have an x plus 3. Or x minus 3, excuse me. Okay?
they have to match.
They have to match. That's what part of being a common denominator is matching up. Now, next thing to do is multiply out the tops. So that'd be 4x minus 20 plus 6x minus 18. All of that is over that common denominator, x plus 5, x minus 5, x minus 3. And then put the like terms together. We're doing addition because the original problem was a plus, right? 4x plus 6x is 10x. Negative 20 plus negative 18 is negative 38. The denominator hadn't changed any. X plus 5, x minus 5, x minus 3. So look at another one. 7x squared plus 4x minus 5 plus 10 over x squared minus 25. All right. Well, this is where it relates back to the factoring stuff, because you have polynomials in the denominators that can be factored, because we want to end up looking like this. Right? So let's factor the denominators to see what's the same and what's different about them. We know they're different, but there may be some similarities. So that's where the factoring comes in. So let's factor x squared minus 25. It's a difference of squares, because 25 is 5 squared, right? That would be x plus 5, x minus 5. That's how that factors. How does x squared plus 4x minus 5, how does it factor? That x method, multiply to be negative 5, add to be 4. -1, and +5. So my factors are x plus 5, x minus 1. This may help you. Notice on the last example, you had trouble with the what's the same, what's different. If you'll go over here and on the side write LCD, least common denominator. That's what that stands for. Least common denominator. Start with the piece that matches. What's the piece that matches? X plus 5. So you know that's in the least common denominator. Then all you got to know is, oh, I got the matching piece already. Now I need one of everything else. What's the everything else? There's an x minus 1, and this one has a x minus 5. So I need one of each of those. So my least common denominator has got to be that. So what you need to do is then look at each fraction and say, what does that one need? What's the first one need? It needs an x minus 5. So I'm going to multiply by x minus 5. What's the second one need? X minus 1. I'm going to multiply by x minus 1. That make it seem a little bit more digestible, maybe? That you just kind of take it and separate it a little bit, and somehow it just makes it make sense. I don't know why. Now, next thing to do, you got the denominators the same. X plus 5, x minus 1, x minus 5. All that, they both got the same denominator now. Next thing to do is do what with the numerators? Multiply them out and then add them up. So we got 7x minus 35 plus 10x minus 10. So that's going to be 7 plus 10 is 17. Negative 35, negative 10 is negative 45 over that denominator. And if you wrote your denominator in a different order than I did, if you put x plus 5, x minus 5, and then x minus 1, that's the same thing. No, you don't have to multiply out the denominator. You can just leave it at that factor form. Not always. They will put the numerator will always be in descending order. They won't. Sometimes they multiply it out. Sometimes they don't. I don't. Because it doesn't have to be. Okay. Numerator should be the right thing. All right. So addition and subtraction. Got to have a common denominator. Got to have a common denominator. All right. Now, that's the first section. We got one more to go. This one's shorter, I promise. May not be easier, but it's shorter.
So this is addition and subtraction, then just goes together.
Yeah, it just goes together. They're all the same. Okay? All right. So it's just 8 o'clock. We got 2 hours here. I don't think it's going to take us that long for sure. All right. This is section 3.5. It's still dealing with rational functions. But it's rational functions now. Graphs. So we want to talk about some stuff with graphs of rational functions. Now, this is going to relate back to translations and transformations that we did in 100. Remember we talked about in 100 if you vertically stretch the graph. My example was the silly putty stuff. If you vertically stretch something, you stretch the silly putty and the image on it gets skinnier and taller. That's what happens there. We talked about horizontal stretching, and we talked about shifting left, right, up, and down. Those are the things we're going to start off with in this section, is talking about those transformations on a rational function. A rational function looks like this. This is the most basic one that we can get. 1 over x. That is the most basic rational function. I'm going to show you the graph of it on the graphing calculator. Really Neat looking graph. It's just 1 divided by x. Looks like that. You got two different pieces. You got this piece here. You got another piece here. There's things in rational functions called asymptotes. Asymptotes are these imaginary boundary lines. There's two imaginary boundary lines for this problem. There's a horizontal asymptote, and see how these blue lines, they flatten out here at 0 on both sides. There's a horizontal asymptote right there at y equals 0. And we're going to learn how to recognize those things from the equation during this session. There's also a vertical asymptote right here at the y-axis at x equals 0. The reason there's a vertical asymptote, it's because that's a restriction on the domain. Because remember, what are the red flags for domain? Can't have a x in the denominator, can't have an x in the square root. 1 over x has got an x in the denominator. If we set the denominator equal to 0, x equals 0, that's where the vertical asymptotes come. We're going to learn that as we go along here. But this is what the basic graph of it looks like. When you start changing that, you can take this graph and you can pick it up and move it up, right, left, up to the left, down to the right. You can vertically stretch it, you can horizontally stretch it, compress it, and all those things. There's a lot of things that can happen to it. All of those things happen, and let's talk about the basics of it, of a rational function. The domain, all x's as long as x doesn't equal 0. For this particular equation, that's what's happening. So that would be negative infinity to 0, union 0 to infinity, if you look at the interval version of that. The range, same idea, it's just y's. Y can't be 0. And that again is negative infinity to 0, union 0 to infinity. Domain's where we're going to hang most of our hat in this stuff. Range, not so much. This one has a vertical asymptote. Asymptote. Vertical asymptote at x equals 0. And it has a horizontal asymptote at y equals 0. And again, as we go through this section, I'm going to teach you how to recognize those asymptote things from the equation. Because sometimes they're hard to see on the graph, but they're in the equation, they're actually quite easy to see. So let's talk about transformations for just a second with this. So we want to describe the transformation of f of x equals 1 over x. So we're going to say, did this move to the left 4, up 6, something like that? Horizontal compression, vertical compression. Remember, things that happen vertically happen on the outside. Things that happen horizontally happen on the inside. So when I say outside, I mean not in the fraction. If I say inside, I mean in the denominator of that fraction. Okay, so that's where this function, the inside and outside are, is the denominator of that fraction. So let's look at this problem. G of x is 1 over x minus 2. A minus 2 on the denominator, so it's on the inside. So that's a vertical or horizontal. It's on the inside. Horizontal. A minus on the inside is going to move it to the right. And I will try to remember to link you to the transformations video from 100 out of that. So maybe that'll help you remember, jog your memory on some of this stuff. Say we had this one, 1 over x plus 5. That plus 5 is where? Outside, so that's going to move it which way? Up, vertically. So up 5. 1 over x plus 3 minus 6. What's the plus 3 inside do there? Left 3 minus 6 on the outside is down 6 units. Left 3 units, down 6 units. So plus on the inside moves it left. Minus on the outside moves it down. Here's the one that kind of disguises itself as weird. 4 over x. Now, that's multiplying by something. That's the same thing. You rewrite it like that. So that's a 4 on the outside. So that's a vertical stretch. Vertical stretch by a factor of 4. When in doubt, graph the thing. Compare it to, on your calculator graph, you got the original graph, go to y equals, go to y2 and graph another one. Graph the new one. So if you graphed 1 divided by, and here's where you got to be careful. If you had x minus 3, you got to put the denominator in parentheses. And see how that moved that to the right 3? So the red one is the new one. It scooted it over. So that you see what's happening there. So when in doubt, graph it and see what's going on. Okay. Let's look at the important parts of rational functions. So we're going to talk about different parts of rational functions in the graphs. Important things in the graphs are the things that I discussed when I first graphed 1 over x. Domain is important. Range is important. Those asymptotes are important. Those are the important things we're going to be finding. Ordered pairs are part of the thing. They're what makes the whole graph up. But we're going to talk about all of these different parts of rational functions. Important parts of rational functions. Okay. Domain. Domain is going to happen before we simplify. Remember, we talked about that in the first section, that you find the domain of a rational expression before you simplify it. So we've got to do that. We want to set the original denominator equal to what? 0. That's how we're going to find the domain. You got to use the original. Don't use the simplified version. You got to find the domain before you simplify. That's important. Okay. The next thing that you start finding is you simplify. Simplify by factoring the same way that we did that in the first section tonight. And we talked about factoring the numerator and the denominator and canceling out the matching pieces. Okay, we're going to simplify. Once we've simplified, then we start looking for asymptotes. We start looking for vertical asymptotes. That's an imaginary boundary. Shows restrictions on the domain and shapes the graph. It's like the fence next to my parents' house. It helped shape the way that I mowed the lawn. Because it was that boundary line, and whatever direction the fence was going, that's the direction that my lawnmower had to go. Okay, so this asymptote is a boundary line. It's going to shape the graph. So it's going to, that graph's going to come up close to it. It's not going to ever touch it. It's going to get close to it. So you've got to look for that. So vertical asymptotes are going to be found next. Vertical asymptotes are whatever is left in the denominator after simplifying. We're going to set that equal to 0. Vertical asymptotes are oftentimes going to match your domain. Things that X cannot be. Won't always be exactly the same. There are times where if you simplify and factor cancels out, you may have more things in your domain that are cut out than there are vertical asymptotes. You may have 3 numbers that are X can't be in your domain, but there may only be 2 vertical asymptotes. They only give you 1 vertical asymptote. Okay? Because when you simplify, your vertical asymptotes come from whatever is left over. See that as we do some examples of that. Okay? Now, vertical asymptotes are if it's a rational function, they're going to be there. You're going to have vertical asymptotes. The next type of asymptote is horizontal asymptotes. They have a condition that has to be met in order to exist. You don't always have horizontal asymptotes. Okay? Horizontal asymptotes only happen if the degree of the numerator is less than the degree of the denominator then the horizontal asymptote is y equals 0. Degree is exponent, highest exponent in the top. If the highest exponent in the top is less than the highest exponent in the bottom, your horizontal asymptote is at y equals 0. Automatically. No calculation needed. It's a memorized fact. Okay? It has another condition that can happen. If the degrees are equal, then the horizontal asymptote is the ratio of the leading coefficients. Here's an example. F of x is equal to x squared plus 3x minus 7 over x cubed plus 5. That one has a horizontal asymptote at y equals 0. This function, g of x, is equal to 3x squared plus 5x minus 1 over 4x squared plus 9 has a horizontal asymptote at y equals 3/4. Degree of this one is 2. Degree of this is 3. Highest exponent. That's all you're looking at is the exponent on the variable. If the top is smaller than the bottom, automatically the horizontal asymptote at y equals 0. On this example, you got squared and squared. They're the same. If they're equal, you take the ratio of the numbers, the leading coefficients. That's the number in front of that variable. So 3/4. That's where the horizontal asymptote is. Okay. Horizontal asymptotes don't always exist. There's another kind of asymptote that can happen. The other kind of asymptote is an oblique asymptote. Part 5 is the oblique asymptote. O-B-L-I-Q-U-E. Oblique, you might hear me say the word slant asymptote. When I learned this, it was called slant asymptote. Oblique, they're slanted. Horizontal asymptotes, straight across. Vertical asymptotes, straight up and down. Oblique asymptotes, they're slanted, either up and to the right or down. It doesn't, there depends on the problem. Okay, so obliques and horizontals never, ever occur together. Obliques and horizontals never occur together. Okay, so but the reason they never occur together is because the rules for them existing. Horizontals happen when the degree of the top is smaller than the bottom. It's y equals 0. If the degrees are the same, it's the ratio of the leading coefficients. Obliques happen if the degree of the numerator is 1 more than the degree of the denominator. Then there is an oblique asymptote. It's going to be a slope-intercept form equation, y equals mx plus v. It's going to be found by doing long division. Long division of polynomials. We'll do example out of that, out of all these in just a second. Five examples. Okay. Again, make sure you make a note. No horizontal or oblique if degree of numerator is more than 1 greater. So it's possible that you don't have a horizontal or an oblique. If the numerator had a degree of 4 and the denominator had a degree of 2, then you don't have a horizontal, you don't have an oblique. Okay? You just have vertical asymptotes. It's possible to not have horizontals and obliques. Verticals you're going to have. If there's x's in the denominator when you simplify, you're going to have verticals. Okay? Obliques and horizontals only occur these certain rules, and you got to know those rules. Do that. We're going to do some examples and just try to build all these things. We're going to look at the graph on the calculator. I'm not so interested in you being able to hand graph one of these jokers, because that's not easy to do. But if you can find all of these parts, the graphs are, doable by hand. Okay, so again, no horizontal or oblique if the degree of the numerator is one more, or is more than one greater than the denominator. So that'd be like an x to the third over x, or x to the fifth over x squared, something like that. You're not going to have either of those. The other thing that we mentioned was horizontals and obliques never occur together. If you've got horizontals, you're not going to have obliques. If you got obliques, you're not going to have horizontals. They never occur together. Next 5 examples here are going to be us working toward getting these pieces out of this. So things we're going to be looking for are, we're going to state the domain and find all asymptotes. That's our job. State the domain, find all the asymptotes that go with this thing. Okay. All right. Let's get an example. Here's the first function for doing all this stuff. X plus 1 over 2x squared plus 5x minus 3. So first thing you want to do is find, it says state the domain, is set it up to find the domain. How do we find the domain of a rational expression? We did that earlier. Got to set the bottom equal to what first, though? 0. So to find the domain, I bumped it. Sorry. To find the domain, you got to take the denominator and set that sucker equal to 0. So 2x squared plus 5x minus 3. Set it equal to 0, and we're going to use factoring to solve that. Okay? Because we know we're going to use that factoring to simplify if possible. So we're going to factor out of that. So I'm going to factor that with the x method. -6 on top, 5 on the bottom. That'd be 6 and -1. Is that right? Yeah, so 2x squared minus 1x plus 6x minus 3. And I'm going to group that. The x, 2x minus 1, 3, 2x minus 1. So the factored form of that is going to be x plus 3 and 2x minus 1. So that factored form is going to come in handy in a little bit. We're still not done with the domain, though. We've got to set each of those factors equal to 0 and solve them. So x plus 3 equals 0. So that's going to be -3. And 2x minus 1 equals 0. It's going to be 1/2. Our domain, then, is all x's as long as x does not equal -3 or +1/2. Interval notation for that would be -infinity to -3, union -3 to 1/2, union 1/2 to infinity. There's our domain. Now, when I look at the factored form of this, x plus 1 over x plus 3, 2x minus 1, does anything cancel out? No. So it doesn't simplify any, which is fine. It's not always going to simplify. Sometimes they do, sometimes they don't. It's actually easier if they don't. Because now that allows me to find my vertical asymptotes. The vertical asymptotes, and we're going to abbreviate that from here on out as the VA. So anytime when I say VA, I'm talking about vertical asymptotes. They match the domain the same. Vertical asymptote at -3 and x equals 1/2. Those are the two vertical asymptotes. There's two of them on this one. X equals -3, x equals 1/2. They are equations. They're not just numbers. Domain happens to be the same too because this one didn't simplify. If it had simplified, you might not have as many vertical asymptotes as you do restrictions on your domain. Okay, it just depends on the simplifiers. We'll see that as we do some more examples. Okay, so we have vertical asymptotes. The next thing to look at is horizontals or obliques. Okay, so the rules are that if we look at the degrees of the numerator and the degrees of the denominator. Because it didn't simplify, we can go back to the original one and say, okay, well, what's the degree of the numerator? 1. There's a 1 exponent on that x. What's the degree of the denominator? X squared, so it's 2. So the top is smaller than the bottom. The degree of the numerator is less than the degree of the denominator. Which one of our asymptotes does that fit? The rules of. So rules for obliques were that the top had to be 1 more than the bottom. That means the top's got to be bigger. That's not what's happening here. So it can't be obliques. Horizontal, if the degree of the numerator is less than the degree of the denominator. Is 1 less than 2? Yes. That horizontal asymptote is at and we'll abbreviate that HA from here on out, is at y equals 0. The oblique, because we have a horizontal asymptote, what's that mean about the oblique? You can't have one. And then we'll call those OA from here on out. There aren't any. If you've got a horizontal asymptote, no way can you have an oblique. If you've got an oblique, no way you can have a horizontal. One or the other, or neither. It's possible that you don't have either. Okay? It's not a lot of the same stuff we've been doing here. Let's look at another one here. F of x. Let's do 4x minus 2 over x plus 1. Very simple one, but it still shows the rules on the asymptotes. Okay? Good news is when we do our domain for this one, we just set x plus 1 equal to 0. Is there any factoring to do? Not on this one. So I just got to solve it for x. -1. So domain is x as long as x doesn't equal -1. Negative infinity to -1, union -1 to infinity. So there's our domain. Our vertical asymptotes. Well, the bottom part didn't factor. What about the top part? It'll factor with the 2, and that leaves us 2x minus 1. But does anything cancel? No. So our vertical asymptote is going to match what we got when we found our domain. Our vertical asymptote is going to be at x equals -1.
So what do you have to use?
The interval notation for domain. We're leaving, x cannot be -1. You gotta skip it. That's what that means. Now, the next thing to look at is the rules for horizontal or obliques. Okay, what's the degree of the numerator? Plain x, it's a 1, right? What's the degree of the denominator? 1. They're the same, right? Which one of those does that fit, horizontal or oblique? Or neither? They're the same, they're equal. Look at your rules. Read your rules. If the degrees of the numerator and the denominator are equal, it's the ratio of the leading coefficients. So the leading coefficients here are 4 and 1.
So it's horizontal.
So it's a horizontal asymptote at y equals 4 over 1. Because it's equal to, so it's y equals 4. That's what that simplifies to be. Because it's equal to. If the top is smaller, it's 0. If it's equal, it's the ratio. Okay? So that means oblique asymptotes, again, would be none. Because we had a horizontal. You can't have those together. Horizontals and obliques do not happen at the same time. All right. Let's do this one. F of x, x squared plus x over x minus 1. So first thing we're going to do is find the domain by doing what? Set what to 0? No. X minus 1. The denominator. Set it equal to 0. We get x equals 1. So our domain is x's as long as x isn't 1. So that means we're going from negative infinity up to 1. Hop over 1 to infinity. Now, let's get a look at, does it simplify? So the denominator doesn't factor, right? But does the top, the numerator?
Yeah, x squared.
You got x squared plus x. So go through your run of the rules for factoring. That's in descending order. What's the GCF? X. So leave in parentheses. X plus 1. Does anything cancel? No. So that means our vertical asymptote is going to be the same as our domain, x equals 1. See one in just a minute where something does cancel and we see something different happening. Now the next thing to look at is horizontal asymptotes or oblique asymptotes. Why? So that means if there's an oblique, there can't be a horizontal. So horizontal is none. Oblique is right for this one because x squared over x, that's 1 more than the bottom. Now, the way that we find that oblique asymptote is we do long division for polynomials. Okay? So we're dividing x minus 1 into the numerator, x squared plus x. Been a while since we did this. We did it back in 100. We had to divide a polynomial. So we look at the stuff in the front. What times x would give me x squared? X. Distribute. and subtract. X squareds go away. X minus negative x is 2x. Technically, there's a plus 0 that comes down there. What times x gives me 2x? Do I need another x? No, I just need a plus 2. And then that'll give me 2x minus 2, and I subtract. These cancel. Doesn't really matter what's happening here. Because our oblique asymptote, remember, it's going to be slope-intercept form. We already got enough for slope-intercept form. So when you do that division, it's got to have, it's going to end up being a slope-intercept form piece. That's your oblique asymptote. Let's look at the graph and show what an oblique looks like. Okay, so I'm going to look at the graph of this equation. Yes, absolutely. After you do 2 steps in the long division, that's all you have to do. The rest of it doesn't matter. Okay. So parentheses x squared plus x, close parentheses, divided by parentheses x minus 1. And hit graph. I can tell this one has an oblique by the graph, because you can see the slant to it, right? If it had a horizontal, this wouldn't do this. It would flatten out somewhere. We can look at the graph and kind of tell what it should have. Now I'm going to graph that oblique asymptote along with this. So it was x plus 2. Graph. Look how this is what that oblique asymptote looks like. It was an imaginary line. So it would kind of be, if you had to hand draw this, it'd be a dotted line like that. Look how that graph hugs up against it. That's what that oblique asymptote does. The vertical asymptote is here at x equals 1. That would be right here. You see how that line hugs up against that. That's what those asymptotes do. They shape that graph and kind of bend it into the right shape out of that. That's what's happening with these rational functions out of that. Okay. All right, let's look at another one. Two more. That's all I got. 2 more. Hang with me. The light, it's going brighter at the end of the tunnel, guys. We can do it. I know this is heavy lifting tonight. 6x squared minus 150. All right. Now, I can look at the original problem and tell something about obliques and horizontals right now. Why is it horizontal? It doesn't matter if it simplifies or not. If the original looks like this and we got the same equal one, I know I'm having a horizontal asymptote at the ratio of the leading coefficients. So my horizontal asymptote.
What was that you just said?
I said just in the original one.
Okay.
It doesn't matter if it simplifies later on or not. If I look at the original, I look at the degrees. The top is the same as the bottom. The rules are for asymptotes, if the top has the same exponent as the bottom does, the biggest one, then there's a horizontal asymptote at the ratio of the leading coefficients, 3/6, which reduces to be 1/2. So we know before we even start doing anything else that there's a horizontal asymptote at y equals 3/6, which reduces to be y equals 1/2. That's what happens. And that tells us that oblique asymptote, there can't be one. If there's a horizontal one, there cannot be an oblique one. They do not happen together. All right. Next thing, all right, so let's go back to the original. What do I do first? Set your denominator equal to 0 so we can find the domain. So 6x squared minus 150 is equal to 0. How do I want to solve that? There's a lot of ways, but what's the way that's going to be helpful for other things? Factoring is the way that I need to do that to make it helpful for simplifying. Okay, so if I factor that, I look for a GCF between 6 and 150. My thinking is, okay, 150 is a pretty big number. I wonder if 6 goes into it. So I just go to the calculator and say, well, 150 divided by 6. It works. 25. 6 is the GCF, x squared minus 25. And then, how does x squared minus 25 factor? It's a difference of squares. X plus 5 and x minus 5. Then, to find my domain, I set anything that's got a variable equal to 0. What happens to this 6 out here when I'm doing the domain? Does it matter?
Sure.
No, it doesn't have a variable, so it's just hanging out, watching what's happening. Okay? Kind of like Congress. Not really doing anything. All right. Now, so we got x plus 5 equals 0. X minus 5 equals 0. Apologies if you're related to anybody that's in. They do a lot. Most of us know good. But they do a lot. Set those equal 0, solve. So x is equal to plus and minus 5. X equals negative 5. X equals positive 5. So our domain are all x's as long as x does not equal plus or minus 5. Now, here's where we've got to go back and say, okay, well, does this simplify any with the original? So if I go back up here and I use that factored form, I've already got the factored form right here. So the bottom part is 6, x plus 5, x minus 5. I'm going to try to factor the numerator. I don't know if it will or not. I'm just going to try to do that. So I've got 3 times negative 7, because I'm using the x method, be negative 21, and it's got to add to be 5. The things that I know multiply to be 21 are 7 and 3 and 21 and 1. That's the only options I have. Neither of those would work out to be a 5, no matter what I do. If I do negative 7 and positive 3, that works out to be negative 4. If I do positive 7 and negative 3, that's positive 4. Still not 5, though. 21 and 1 is worse. It's 20. Or negative 20, whichever way you do it. It doesn't give you 5. So what's that mean about the numerator? It stays that way. It does not factor at all. So what that tells us is that the vertical asymptotes are the same as the pieces of the domain. Vertical asymptote at x equals negative 5, x equals positive 5. How do you verify that? Look at the doggone graph. Okay. That's a little rain. So look at the graph of the thing. We should see this line with something happening at positive 5 and at negative 5. So if I look at the graph, I've just got to be able to type the thing into my calculator the right way. So that's half the battle here. So I'm going to clear out this other stuff I've got. What you've got to do is you got to put parentheses around the numerator. So parentheses, and then we're putting 3x squared plus 5x minus 7 divided by parentheses. And then the denominator, it didn't simplify any, so I'm just going back to the original because it's quicker to type in. That's the only reason I'm going back to it. So 6x squared minus 150. It's exactly the original. So I'm hitting graph. Look what's happening here. 1, 2, 3, 4, 5. Line. We'll go here to negative 1, negative 2, negative 3, negative 4, negative 5. We see something happening there. We see that that's what's going on. with this one. Horizontal asymptote at 1/2. 1/2 is about right there. You see that happening? Looks about right. Graphs can cross horizontal asymptotes. They can't cross vertical asymptotes. They can cross oblique asymptotes, but they can't cross vertical asymptotes. So sometimes you might see your graph kind of crossing a horizontal asymptote or crossing an oblique. They can do that, but they can't cross vertical ones. All right, so it's like electric fences. 3-strand electric fences are very difficult to cross. Those are like vertical asymptotes. 3-strand barbed wire fences are very easy to cross. Much easier than 3-strand electric fences, right? So those are like obliques and horizontals. Okay. So. Yeah, I would take that. That's fine. Yeah, that's absolutely fine. Out of that. Good question. All right. Let's do one more. I don't know what letter we're on here. I. Good one to end on. Let's see here. Let's do x squared plus 7x plus 12 over x cubed plus 4x squared. That's good. Okay. Let's get our domain. Setting x cubed plus 4x squared equal to 0. Again, what method are we trying to use to solve this thing? Let's just set it out. So, I got to teach you. What method? Factoring. That's what we want to try to use. Well, how do we factor that? And okay, x squared is the GCF, leaves us x plus 4 in the parentheses. We set each of those factors equal to 0. What squared gives me 0? 0. So x is equal to 0. And this one be x equals -4. So our domain is all x's as long as x does not equal -4 or 0. So interval notation for that would be -infinity to -4 union -4 to 0 union 0 to infinity. What do we know about horizontal or oblique asymptotes? Where? The top is less than the bottom. So that means the horizontal asymptote where? Where's it at? Nope. It's in one spot. The rule today. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at y equals 0. So it's at y equals 0. Now, gotta do vertical asymptotes. We don't have an oblique. We have a horizontal. We've got verticals somehow. So we've got to look at factoring everything. So top part, we got x squared and x plus 4. Bottom, or excuse me, that was the denominator. Numerator, how does x squared plus 7x plus 12 factor? X method, got to multiply to be 12 and add to be 7. 4 and 3. I can take the shortcut. It's x plus 4, x plus 3. What cancels out? The x plus 4's cancel. So my simplified version has x plus 3 over x squared. So my vertical asymptotes, I don't have the minus 4 anymore because it canceled out. My vertical asymptote, the only one I have is at x equals 0. That's what happens when you have a cancellation and it simplifies, one of your vertical asymptotes goes away. What ends up happening to the graph, we'll talk about this next week, is there's a hole that exists at that x value. At -4, there's an empty circle on the graph, is what happens with that. We'll talk about that some next week and get a little deeper into solving some of these equations. All right, so we got a vertical asymptote at x equals 0. If you look at the graph, I can do x squared plus 7x plus 12 divided by x to the third. Give me my equation back. There we go. X to the third plus 4x squared. Hit graph. We can see that vertical asymptote there at 0, and we don't see 1 happening at -4. Right, so we know that that's where that is here. That horizontal asymptote is at y equals 0. Notice how this crosses that. Remember, you can cross horizontal asymptotes, you can't cross verticals. So it's okay if it crosses a horizontal or an oblique when you look at the graph of that. But that's what's going on there. So stuff takes a little bit of practice. It's not the easiest of material. Like I said, if you can make it through the next couple of weeks without quitting on me, you can. So R.5, just 1 through 78, just some of those. 3.5, like 100 and something problems that you can pick from in the textbook to work with. So you got a Canvas quiz that covers some of this stuff. Again, 2 opportunities to take that and take your highs. And then next week we'll do some more with rationals. So it's everything rational. It's in this section or in this test that we take right before spring break. The good news is you take that test, you got 2 weeks of really do no math to do. When you get a good break in there, barring any kind of weird weather thing happening between now and the 25th of February. If you got questions, please email me. I know it's probably going to have some of this stuff just because it's difficult. I'll try to link videos to you in Canvas messages, and that way you've got some stuff to kind of help you support you a little bit. So, let's have a great week. I'll see you for the first week. I don't have them very. When will I? Hopefully tomorrow. I graded a ton of stuff today, so hopefully tomorrow. You'll be all right.